Okay, this is our last theorem in the finite field chapter. Here we go. The irreducible factors of x to the p to the e minus x, which just lives in fpx, are exactly the irreducible polynomials in fpx whose degree d divides e. Okay. So this actually says something kind of weird. Like, let's say we wrote down, so in particular, right? So here's just an example. Let's say we do x to the p to the 2 minus x. This factors, well, we know a bunch of the linear factors. These are x times x minus 1 times x minus 2 times dot 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 x minus p minus 1. And then we're going to have a bunch of quadratic factors. Quadratic because L, because the degree of each one of these has to divide 2, because that's the E here, right? That's my E. Where the Fi of x are the irreducible degree 2 polynomials. So, over Fp. Okay, so for example, if you wanted to find out how many irreducible polynomials over Fpx there were, well, you could just compute this degree right here, and these are all degree 2. So you just have to do a little bit of arithmetic. I'll leave that to you. There are actually some exercises which I didn't assign which go into that direction. Okay, but this is pretty cool. And each one of these FIs is also going to show up exactly once in this product. All right, so we need to prove this theorem. Okay, what's the idea? Proof. If f of x divides x to the p to the e minus x, and f of x is irreducible, I need to show that the degree of f of x divides e. But remember, we had this previous theorem that the subfields of fp to the e are exactly the fp to the d's, where d divides e. So let's say, okay, we know that f of x divides xp to the e minus x. So since this one splits completely in fp to the e, say alpha is a root of f of x in fp to the e. Okay, we know that this thing splits completely into linear factors in fp to the e because that's how we made fp to the e, basically. So alpha has to be, so f of x also has to split completely up there. So let's just let alpha be a root. Right? Then we have fp inside fp alpha inside fp to the e, just by construction. And this degree has to divide that one, just like we've seen previously. So degree of f of x, which we might also write as the degree of alpha, divides the degree of this, which, as we've seen previously, that's e. Okay? So if I have an irreducible polynomial dividing this, then its degree must divide e. So that's half of what this theorem says. Conversely, let's suppose g of x is some irreducible polynomial of degree d, where d divides e. We want that g of x divides x to the p to the e minus x. Okay, so what are we going to do now? All right, so I think the idea is let's let beta be a root of g of x in some extension of fp to the e. I'm sorry, or I was what would you say fp now? Okay. Now, if I know that extension, I guess I should give it some extension k of fp. Now I know k, if I do k over fp, that's just going to be the degree of my polynomial, so that's going to be d. Okay, because remember, we just assumed, k is just, sorry. fp beta colon fp, this one is d. I don't know anything about that extension. That extension was just some random extension out there. Okay. Okay, but this means by our uniqueness, thus, fp beta is actually isomorphic to our magical fp to the d. And this one lives inside fp to the e, because d divides e, and that's what we proved in the previous video. Okay. All right. So what do we do now? Well, there is some element that beta maps to in fp to the d, called beta prime. I don't know what it is, but that beta prime is also going to live in fp to the e. Since beta is a root of g of x, so is beta prime. Because this isomorphism here doesn't do anything to the underlying fp, where the coefficients of g of x come from. So since beta is a root of g of x, so is beta prime. So g of x has a root in fp to the e, right? But we know that beta is also a root of xp to the e minus x, because everything in fp to the e is a root of xp to the e minus x. And so since g of x is irreducible, it's the minimal polynomial. Whoops, not beta prime. So beta prime is also a root of x to the p to the e minus x. So since g of x is the minimal polynomial for beta prime, since g of x is the min poly for beta prime, g of x has to divide x to the p to the e minus x, and we are done. Okay, this finishes all our lectures on finite fields. We'll briefly cover primitive elements early next week, but then we're moving right on to Galois theory by Wednesday of next week, if not sooner. Okay, hope to see you on Zoom or Skype or whatever in an upcoming class. Bye.